something called variable time step, meaning that if you use very fine sampling time, it takes long time. But if you use long sampling time, it'll be faster, but there will be error. Okay, so be careful with using solver. Okay. Anyway, so if you move on to two-state second order system, now what happens? Well, start from F equal ma. If we are interested in both speed and position, then it becomes two-state as second order system. And this, we can express these in matrix form, right? And then we can set it up like this and then solve for x, right? And if you put this into Matlab will solve x for you using solver. Okay. Okay, that's a quick tutorial of Matlab and Simulink solver, which not many students pay attention to. Okay. But you need to understand what's running behind it. Okay. Okay, now let's look at the model, the parallel hybrid model. Okay, so this model will be distributed to you. Okay, so you can start from somewhere for homework and maybe for your term projects. Okay, so if you open this Simulink block, you will see this block diagram, and you will be able to find driver model, controller, engine, motor generator model, then battery model, and then transmission model, and then vehicle dynamics model. Okay, and this plant, this hybrid electric vehicle powertrain, needs 5 control inputs, which is use 5, and then 1 drivability constraint, meaning that 내일 네, 네. 제가 하겠습니다. 네. Sorry about that. So we need to get the controller needs to generate this 5 control signals to control engine, motor, transmission, and vehicle, right? And we're going to look at how each component is modeled. So we already looked at this model in the vehicle dynamics part. This is just a quick summary of that. So for the vehicle dynamics, oh, by the way, in this parallel hybrid HEV powertrain model, there are 2 states: vehicle speed and state of charge. Okay. Everything else is static, meaning that it's algebraic equation. I mean, it may be nonlinear, but they are algebraic equations. Okay. So there are only 2 independent dynamic states, which is vehicle speed and state of charge. But later on, we will find out this V will be constrained by the drive cycle. Okay. And if we look at the vehicle dynamics model, we basically have point mass dynamics, one-dimensional model, because we are only caring about the speed and position, right? So it's F equal ma, where F consists of driving force, braking force, and then resistance. Okay, and resistance has three terms, right? And this is driving force, which is coming from the powertrain. And then we have brake, right? If we look at road load resistance more closely, this is what it looks like. So there's aerodynamic drag. There's if there's a slope, then there will be gravity acting backwards, which is another resistance. And then there's a rolling resistance, or sort of viscous losses. So, and combination of all of this will end up having some coefficients for each term. Okay. So in industry, in automotive industry, people talk about these values when they are testing road load, and when they're simulating fuel economy, they must know these values. And this depends on the target vehicle. Okay. So whether it's Avante, Sonata, Santa Fe, different vehicles have its own these road load coefficients. Okay. Once we find these values, if we plot, it looks something like this. Okay. And with increasing grade, slope, it increases. And by the way, obviously we want to minimize this term. I mean, we want to minimize all the terms, but these are very important, right? Oh, by the way, this is 2. Because with increasing speed, this term increases quadratically, right? So F2 should be minimized. I mean, F1, F0 should be minimized, but the impact of F2 and F1 is bigger, right? At higher speed. And the drive line looks something like this. So here is acceleration. This is V. This is distance, right? So basically, here is force. And there's drive force, brake force, and roll load. The summation of that is total force. And if you divide it by mass, then you get acceleration. Integral, you get speed. Integral, you get position. Okay, simple. Transmission. Let's look at transmission. Transmission is in this model, it's quasi-static model. Okay, it's static model. So there's no dynamic states. So there's only algebraic relationships. Okay. And note that the input is torque, input torque, and output speed. Okay. This is interesting part. Okay. Output speed is input to the transmission model. Okay. And once you select gear, the gear ratio is multiplied or divided by for each term. Okay. And here. Okay. And we have two parts for the torque model because efficiency has to be inversed to make sure efficiency is lower than 1. Okay. So whether it's driving or driven, the efficiency has to be inversed to make sure efficiency is lower than 1. Okay. And now let's look at engine model. So engine model has two parts. One is torque and the other one is fuel consumption. So once you command throttle, you can compute torque and fuel consumption. So fuel consumption and torque, each module, each block has these two maps. Okay, this is torque map, this is fuel map. And engine torque has this nonlinear map, which is function of speed and throttle. Okay, and fuel consumption rate is also function of theta and engine speed. But again, remember, engine map is static map. Okay, but in reality, engine does have dynamics, but engine dynamics is neglected in this study for high-level energy management problem, for simplicity, to make the simulator fast and use some of the optimal control theories. Okay, but if you want accurate model, you need to include some of the dynamic states in the engine model. Okay. But here, torque is directly used, right, for driveline. How about fuel consumption? Well, how do you compute fuel consumption? What is the definition of fuel economy? Usually it's either kilometer per liter or miles per gallon, right? Or 100 liter per kilometer. In order for you to compute fuel economy, you need to compute how many miles or kilometer you have traveled. Oops. From here, distance, right? What other information do you need? You also need how much fuel is consumed. And to compute that, you need to also take integral of this rate, fuel consumption rate. Then you get fuel consumption. Okay. And motor generator, again, it's a efficiency map. It looks a little complicated, but there are mostly constraints to make sure the motor is operated within the feasible operating region. But the key part is this one, okay? This is motor map. So you take speed and torque and you compute efficiency to compute how much power, how much electrical power is needed, okay? When you have, this is true, the final torque, and this is the motor speed. So if you have these two, then you have mechanical power, right? Again, right? But once you multiply this by efficiency, then this becomes electrical power, right? Because input was mechanical torque and speed, and output, what we are trying to compute here, is electrical power consumption, okay? And this is that, PNAT, okay? These are just constraints, okay? This is what it looks like, efficiency map. And next, let's look at battery model. So battery model takes the electrical power, which is the output of the motor, okay? So motor computed how much electrical power the motor consumes, and that goes into the battery. And battery computes state of charge, okay? And I already talked about this slide at the beginning of the lecture, so I will move quick, okay? But basically, the way this works is, this is battery power request. from the motor, which is output of the motor. And based on the power, you compute, make sure that command is feasible. And then for that value, you have to first compute open circuit voltage and resistance value, which is a function of SOC. And then using open circuit voltage and resistance value, you compute current. So you have battery power, you have resistance, you have voltage, you have all the information you need to compute battery current. And using that current, we can compute SOC dot and SOC finally by integrating current over time. Okay. And this is shift logic, transmission controller. I'm not going to spend too much time here. Okay, I'm going to move fast. But there are also, two shift maps. One is upshift, and the other one is downshift. We could have EV upshift and EV downshift, but usually these two are similar. I mean, we can make it different and improve efficiency, but in reality, in real products, one shift map is used for upshift and downshift. And the way this shift algorithm works is we have the blue line is upshift and red dotted line is downshift. So they're not identical because we need some hysteresis to avoid frequent shift. For example, if we increase speed, when we are increasing speed, accelerating, vehicle will upshift at this point, but your vehicle speed may have this dip, right? But if you did not have hysteresis, you will upshift and downshift too frequently, right? So you need this hysteresis, some space between up and downshift. Anyway, so this is first gear, second gear, third gear, fourth gear, okay? X is vehicle speed, Y is power demand. How much driver wants power? So if you step on the gas, if you throttle, then at say 40 miles per hour, then you're increasing power demand. So here you have to downshift. Okay, you're in fourth gear, but then if you go to this area with increased power, then you have to use third gear. Okay, this is called shift map. Okay, and then time is up. I will finish here, but please take a look at the rest of the slides. Tuma, when are we? Did we inside of the controller, we have this shift logic. Remember, this was a parallel hybrid with conventional transmission. So we need a shift logic that can optimize fuel economy and driving performance depending on the state and power demand. And inside of the shift logic, we have shift map, which looks something like this. So we talked about what happens when vehicle speed increases or when power demand changes up and down. And then, and now we're going to look at the drive module, meaning that the HEV controller for driving mode, meaning acceleration mode. We also have brake module, which we'll talk about it later. So inside of the driving module, it has two subsystems, two submodules. First one is power management control. The other one is engine optimal control. And the input to this driving module is these three: engine torque, power demand, and then transmission input speed. And the output we are trying to determine here is motor torque and engine on-off command and engine throttle. So how do we find these values? I mean, we want optimal values, right? We want to optimize these outputs of the controller. So the way this works is that we first compute torque demand at the transmission input, and then using that torque demand, we're going to compute engine torque. And using engine torque and power demand and input speed, we're going to determine these two. And inside of the power management controller, this is one example of a power split strategy for parallel hybrid. But this is not unique, right? There are different ways of designing this module. And then once we determine what the torque demand is, we can determine motor torque using engine torque, right? So try to understand conceptually what's going on. So we determine torque demand, and using the drivability constraint, we can determine motor torque, and then to provide torque demand, we're going to determine engine torque. And then we need throttle value to produce that engine torque, okay? And then the brake module. We'll talk more about the power split um, strategy later on. Okay, just showing you how different control modules are connected with each other and plants. Okay, and the brake module is used when power demand is negative. Okay, when driver model requests for minus power demand, that means braking. So we need a braking module, braking controller to blend um, uh, re region motor-based recuperation power and friction brake power, right? And this is how it looks like. It looks complex, but it's quite simple conceptually. So what's going on here is, so this is a driver power demand, which is negative. And we want to determine how much motor torque should be applied and how much friction torque should be applied. By the way, this one is before transmission, but this one is at the wheel. Okay? So you need proper gear ratios to switch between those two. Okay? Anyway, to determine these two values, we need a strategy, so region strategy. So to explain that better, this let's start with this one first. There are two, I mean, there are different ways of blending friction brake with region brake. Okay, we basically have to, you know, blend them because motor cannot provide all the torque and power, braking power driver wants. Motor power is relatively small, and if driver asks for high power brake, then friction brake has to come in. And these two are just two examples of how to blend them. Okay, the first one is parallel, and then the second one is serial approach. Parallel being you always blend motor and the friction brake at any time as a function of brake position. I mean, you might you could change the blending ratio a little bit, but you do blend them by this much. Serial approach, the idea behind serial approach is that let's use motor regen as much as possible, okay, or up to a certain level. So up to this level, use motor regen to brake. But when driver asks for more brake, the rest of the torque or power will be covered by the friction brake. I mean, yeah, friction brake. So which one do you think is better in terms of efficiency? Anybody? It's a simple question. 준태 학생.
네. 리젠 효율은 시리얼 쪽이 더 좋을 것 같습니다.
잘 안 들려요.
리젠 효율 자체는 시리얼 쪽이 더 좋을 것 같습니다.
좀 더 가까이에서 크게 얘기해 주시겠어요?
리젠 효율 자체는 시리얼 쪽이 더 좋을 것 같습니다.
네, 왜 그렇죠?
일단 더 많이 개입을 한다 그래야 되나? 브레이크 페달 포지션이 낮을 때도 대부분이 이제 모터를 통해서 있으니까 일단 그냥 그래프상에서 영역이 더 넓어서 그렇게 본 것 같습니다.
Anyone else wants to explain? 재윤 학생 어디 갔나요? 현호.
네.
네. 어떤 게 에너지 효율 측면에서도 좋을까요?
시리얼 모드가 더 좋을 것 같다고 생각한 게 감속할 때 가속도가 작을 때 패러렐 모드는 항상 브레이크가 개입을 하는데 시리얼 모드 같은 경우에는 브레이크를 개입하지 않고도 제너레이션만 통해서 제너레이션을 통해 가지고
뭐죠?
네. 갑자기 시리가 켜졌습니다. 네, 그래서 시리얼이 더 좋을 것 같습니다.
네, 맞습니다. 시리가 도와준 거 아니에요? 네. 효율 측면에서 시리얼이 더 좋습니다. 왜냐면 기본적으로 그 아이디어 자체가 serial approach 있네요. The serial approach is better in terms of fuel economy or system efficiency because it tries to approach the idea behind serial approach is it tries to recuperate as much as possible, meaning that friction brake doesn't come in if motor can regen the braking torque, and friction brake only comes in when motor cannot recuperate energy. But parallel does not do that, meaning friction brake is also blended at low power, low torque conditions. But the disadvantage of serial approach is that around this boundary, when friction brake comes in, you might feel some, some vibration, or you know, you may not feel comfortable with the braking feel, because the service brake will start engaging, and that can introduce some disturbance. But when you blend all the time, it's easier to control service brake, and this boundary is not as abrupt as series approach. So going back, the motor, basically we are trying to determine how much motor torque it should be commanded, will be determined by this function, where WSOC and WV is weighting function, and we're going to select the minimum of torque demand, or maximum motor torque, or maximum battery torque, meaning that maximum torque that the battery can provide. Okay, and if these two weighting function looks something like this. So this is SOC, and this is vehicle speed. Okay, so what this is doing is that when SOC is really high, then weighting function makes sure you no longer recharge your battery. Okay, and when vehicle speed is very low, you also decrease the regen, because at low speed you may feel a large jerk when you try to recuperate using motor. On the other hand, the amount of energy you can save, recuperate, is low at low speed. Okay, so usually, okay. And this one is a very nice figure that summarizes how motor power and friction brake should be blended to optimize or to maximize energy regen. Okay. For example, X is vehicle speed and Y is brake force. Okay. And this line is how much is designed, or how much the vehicle, how much the amount of total braking force the vehicle can provide. In that case, this will be covered by the motor, and the rest will be covered by friction brake. This is just same figure, but sort of reversed. Does this look familiar, this line? Doesn't this look similar to motor map? Yeah, so this is motor map, or maximum torque line of a motor, right? So when driver asks for more braking force than what motor can provide, then friction brake has to come in, fill that gap, right? So this is how much friction brake will provide. This will be how much motor will provide at this vehicle speed. But as vehicle speed drops, motor can provide more torque and friction brake can be reduced. What does that mean? From energy and power perspective, remember this line is constant power line, okay? So this and this is same power, but if you operate at lower speed and if you apply low braking force, then most of that energy can be recuperated. So if you are driving hybrid, you need to be soft on the brake, okay? That will help you increase fuel economy. If you do hard braking, then friction brake comes in and you're losing that energy, okay? And this is the simulation results. Have you guys played with Matlab Simulink file package? So if you run, you should be able to see these plots, okay? This is just zoomed view of, I think, yeah, from 0 to 250. The first few cycles, okay? And here you can see how engine and motor are blending its torque, right? And this is engine on. This is engine off, right? So when engine is on, the green one is engine, and then the red line is the power, motor torque, and the blue one is total engine plus motor torque. So when you're producing, when engine torque is higher than total torque, then you need to recharge, or you can recharge and use that energy later, okay? Note that engine torque is relatively flat. And we'll see more about this later, okay?